Okay, hi guys, I'm Rozenberg. I'm the CTO and co-founder of VideoFlow. And today I'm going to talk about cloud-based on-demand seamless disaster recovery. And we heard the people before me talking about cloud production, going to the cloud and how is it great to be in the cloud. But sometimes we want to use the clouds to distribute the content down to earth to receiving agents. And let's see what we need to do about it and how optimize cost, delivery, and make it seamless. So this is the outline of my story. We're going to talk about some cloud disaster recovery topologies, some seamless switching for visual impairment, some seamless switching and visual impairment causes, cloud-based RTP seamless switching, and cloud-based UDP seamless switching, which is a new technology that I'm working to develop. So cloud disaster recovery. So as we heard before, my esteemed colleagues here talked about that cloud playout becomes the new norm for most new workflows. That is true, and it's quite evident. We then need to provide also cloud is perfect solution for disaster recovery. Disaster recovery design as its egress cost billable only when it's used. It's a pay-as-you-go when disaster recovery is activated on a destination by destination. We no longer need to push the disaster recovery feed all the time. We can do that on a demand basis. So the playout and disaster recovery may be located at different availability zones or even different cloud providers, if you choose to do so, to optimize our delivery. So let's see what is a typical playout disaster recovery scene. So we have, on the left, we have two availability zones. We have a bunch of receivers and a management system monitoring the reception of all the lines. In these scenario, both the playout systems are sending the content twice, and the client needs to pay for that quite heavily if it's a 24/7 type of operation of broadcasters, TV stations, and more. Another approach is to do that as an on-demand. We will have an active and standby system. One is the primary, sending the content all the time. But now with the cloud, we can go to a standby operation so that we don't have to actively send the backup feed all the time and do that on demand. And as I said before, why do we want to do that? Because we don't want to spend the money for that operation and activate that on demand. If receiver A needs attention, only receiver A will receive a backup feed or disaster recovery feed, and that saves a lot of money in the process. So how things are done today? Well, traditionally we started with no single point of failure. Everything is duplicated. That is the tradition that we've been doing for the last 50 to 20 years. Optionally, we have two different profile delivery. We have a primary, which is a high profile resolution, frame rate, and bitrate. And the backup can be of a lower it can be identical to the primary, but it can also be a lower profile, lower resolution, lower frame rate, because it's just a disaster recovery only when you need that. Usually we'll go for a dual path to a link delivery with the same overall delay to have the minimal switching time. We will use a management system to control who to pick if disaster happens. The switching time will be a few milliseconds, but possible some time difference between sources as they are created from different playout systems, unless the wrist synchronization method will be used, and then it will be a minimal switching. But that is for the future. Short visual impairments when switching back and forth between the sources may happen and cause some interference. Customers needs to pay, customers in that sense, the broadcasters will need to pay for two active paths and associated equipment. So how it will look, just like you know from the past, we have an active, two senders, two systems, two receivers, and a system monitoring. And then if receiver A or B show a failure, it will select the active feed, the suitable feed to continue. And on a timely basis, we will see the primary in blue showing a feed, a secondary, and a switching on the receiving out, showing that we cut over from one to the other and continue from that point on. So there might be a minimal interference, visual interference when switching. Another approach to save, and that is when saving some money, is that we use an active standby delivery. So we still have a primary, which is active, and a second feed is activated only when the primary goes down. For example, cloud availability zone, one is active, the other one is in waiting. Each link has a unique path delay. We are not trying to synchronize any delay. And the management system will monitor the primary liveliness, and if it goes down, it will activate the backup. Switching time may be of minutes because we need to detect that the primary failed and then activate the standby. It will then cause a long visual impairment when switching primary to the standby, but probably a short switching time when we will switch back because the primary is active and we just switch back. It will be a minimal of interference. And the benefit is that we pay only for one active link and allow the backup to be on standby, and we don't incur any cost on that, and that is a huge saving. Okay, sorry. So it will, looking at the previous system, it will look something like that. We have a primary active, the backup is in standby, a monitoring system looking at the primary link, and when it detects a failover, it will activate the sender B, and the receiver will select receiver B, and so on. So this system that is the old workflow, we want to bring that to the cloud to optimize the saving. So this is what happens in time. Basically, we have a primary, we have fault detection time, and then we have standby activation. So that is the time. The total switch time is longer, and there's obviously an interference on the output. So now, cloud disaster recovery. Private case, this is basically a private case for hot standby. We want to have the primary link from the source and a DR site in waiting. The DR is activated by a management system, most often from an alternate source. And just like before, the management system monitors the primary link liveliness and during the switching time, and there will be a long visual effect, and these are two topologies that might happen. So traditional topology would be on the left. We have a sender A, it may be a source, and it has a backup in the cloud. It is in waiting and activated on demand on a receiver by receiver basis. You don't have to send the entire content to all the receivers, only those who are feeling the failure, which may be a localized network or so on. But it also can be in the cloud. So we have a cloud playout, main primary working, feed is sent to a disaster recovery. And if a receiver failed, doesn't receive its primary link, we switch temporarily to the cloud. And it's a very cheap disaster recovery activation and saves the CFO, we make the CFO happy. So another thing that we can consider is to do an on-demand switchover. What is an on-demand switchover? Is basically allow the receiver itself to switch between sources. Take away the management system and try to make the switch simpler. How we will use that? We will use a client-server approach, which the receiver can trigger a client to connection to a remote DR site when the primary link stream goes down. For example, we can use the method of REST, SRT, where they have a client-server approach, and the client is activated to go to the server, create a connection, and when connection is established, then and only then a feed is sent down from the cloud to the destination, And then, so we basically eliminated the management system, and we can do that by ourselves. Many new receiver devices include this functionality within them. They can switch to an alternative source, whether that be RIST, SRT, and so on. And that basically the main advantage is timing. The switching time does not call for a management system, and it saves time. So it will look something like that, like we saw before. So what we see here is that there is no management system. Everything is self-managed. Every receiver manages its own delivery. When primary goes down, it will activate some kind of a call to a cloud DR server, and the feed will come in. Once the primary goes back, it will switch back, and we are done with that. We stop paying money for that egress cost. So the question comes, can we make it seamless switching? Can we kill the impairments when we are switching back and forth? So initially, we can use RTP and SMPTE 2022-7 seamless switching to allow a new kind of seamless switching between links and path, but only if the source is of the same origin. Payload and RTP headers must be the same so that we can utilize seamless switching. This will minimize the need to switch between paths. A management system will be responsible to switch between the source and destination and to make elements. Sorry. Now we can enhance that further by introducing ARC and Loacher. ARC, we mentioned RIST before, and we have other techniques. We have RIST, ARQ, we have SRT that is going to have Loacher and bonding capabilities. In this sense, we will have a single source sending twice using 2 or more ISPs to a multi-interface receiver. There can be multi-interface sender or multi-interface in the sender to a single interface receiver, or there can be a multiple interface server to a multi-receiver. And we can also do Loacher delivery, things that the RIST today can do, and that was demonstrated at the last actual face-to-face VTrans when we showed that capability. Tying up IRQ and Loacher allows to less pressure on the network, meaning that we don't have to send the full stream, but we can also send part of the stream as needed. We can then optimize the buffer delay. Optimized ARQ fine-tuning will be the key for seamless switching. The receiver buffer will aggregate the inputs and address link delays as needed in the buffer, just like Ciro showed in his presentation. Any packet loss on the way will be handled by the ARQ. No output impact when primary returns because we are using Loacher. Excuse me. So hot with SMPTE 2022-7, we can design a crazy system that will send the data over multiple interfaces using multiple paths or networks to the receiver, so that if the network or the sender goes down, we are still maintaining seamless switching to the receiver. So it's a huge benefit. So there are no visual impairments. So just to show how it is done, we have a primary and a secondary, and we can see them blue and green. And because packet getting lost on the receiver, we will see a mix of blue and green going out, and it's a seamless continuous stream. Now, if we want to make it cost effective and utilize the capabilities, here RIST comes into play, and we can see an example of using Loacher, where we basically send 50-50%. Instead of duplicating to, duplicating to and sending twice, we are basically sending only 50% to every link. So that is 100% instead of 200, and we get the same quality. So the outcome will look something like this. On the primary, we'll send one, in this case, 50% once every other packet. On the secondary again. And on the receiver, we will reaggregate that to a full stream that will, with the use of buffer delay, it will be outputted seamlessly and without any glitch. Any packet being lost will be recovered by ARQ. And as I said, this is already available in RIST and was demonstrated, and we are waiting for this to be available with SRT. There are some preliminary libraries available for those who want to test that with SRT today. So cloud, we want to apply this to the cloud, using cloud DR with seamless switching, enhanced with ARQ. In this case, the origin source is sent to the cloud DR to be in waiting. So we have the same source coming from this primary site. A single source sending twice, primary link to all receivers, a backup link would be to the cloud source. So that we have the same reference. Management system will monitor all the receivers for the link failure. The ARQ is used to compensate for the switchover time difference between as soon as a switch is generated, and we will need quite a big buffer delay to allow it to be seamless. The receiver buffer will aggregate the inputs and address any link delay, and any packet loss will be addressed by ARQ. No output impact when primary returns because we have a buffer delay and everything is switching fine. So once again, we're going back to the system, and because we have the top link going from the cloud to the DDR, once we switch over, and this is duplicate, this signal is sent, we can do, hopefully, we can do a seamless switching. The only caveat is that we will need a longer delay because there is a time difference between when we switch, and let's see that. And this is the problem that we have, basically. Once again, we have the time difference between the primary and the secondary as they hit buffer. And this is without an ARQ. What happens with that when you don't have an ARQ? So can we make it seamless using ARQ without EP and ARQ? Problem description is that we have, as I said before, we have a time difference between the activation command and the first packet hitting the receiver from the backup side. It creates a hole that we need to buffer. If ARQ is in use and the buffer is big enough, it may be able to overcome this gap, but it means we need to have a significant buffer to overcome the activation difference. The ARQ report is used only after the first packet hits the receiver. So there's an additional delay. So let's see that. So basically, this is what we now will face. We will have the primary, we have the secondary, we have the hole. And we can see that in yellow, the first packet coming from the ARQ is delayed because only when the red packet hits the receiver, then we can start resending. Now in this diagram, we see what happens if the buffer is not big enough, and what will happen that the hole will, we would still have a hole because the ARQ did not finish to reassemble or resend the missing packets. So that will create a visual impairment. So can we speed up the recovery? Well, the solution that I propose is to use a preemptive wake up of the sender to start sending the stream from the last known RTP sequence number. This is a new technique that is not available today, but is reasonable to add that without any problem to the specification, because it basically uses the same techniques that the RIST or other packets are using. Basically using a ARQ range message that is available in RIST, we can alert the sender to send the packet from the last known RTP packet to an estimated range that will simulate the hole so that we can speed up the retransmission. So it will look something like this. So we can start resending before the first packet hit of the switch. With that in use, we can use a smaller buffer, and we can compensate for the time difference and have a seamless switch. So another question that people ask me, can we do that with UDP? We don't have an RTP, because a general answer would be, well, let's take the UDP, convert it to an RTP, and be done with that. But still some users prefer to use UDP as the main transport protocol instead of an RTP. So in the next slides, I'm going to show how this can be addressed using a UDP. So let's talk about the problems of UDP. UDP header offers minimum of information. It doesn't have any specific sequence number, timing, and nothing. Payload offer almost no indicators to track other than full baseband detection, if we want to do that. Some articles suggest to use an auxiliary information like closed caption or audio to detect a switching point. So if I can track closed caption or audio point, that is a low frequency data that I can track, and I can decide it to be a switching point. But what happens if the data is encrypted? Most implementation will result to no seamless switching with a visual impairment and time difference. So any hot or active is not that feasible. And it's a very simple DR implementation. A new approach for seamless UDP-RTP switching is that we propose to transform the UDP problem into an RTP problem by creating a reference RTP stream from the original stream. Only a reference stream. We are not going to send it because people insist on using UDP. We then will create a manifest list from the RTP reference stream, create markers based on internal payload information, for example, using PCR, PTS, or hash the payload, and more. And then share that manifest with the receivers. At each receiver, we will include an agent that will tune to the manifest list and sync up to the markers against the incoming UDP. Each detected marker will correlate to a reference RTP sequence number. This way, the UDP stream and the RTP stream, reference stream should be in sync. For CloudDR, use the reference stream sequence number to signal backup sender what sequence number to use for the start of the stream. Well, I'm probably talking tons, so let's see a diagram. So in this example, we took a UDP stream. We detected markers. We identified markers that we're going to use to be distributed in the manifest list. And we basically give a sequence number to each packet, while still delivering the UDP stream untouched. So every marker has an RTP sequence number, and we publish that in a manifest list. And we can see below the reference RTP stream. And once again, this is stored internally, the RTP stream. The UDP stream includes the markers, and we send that to the receivers. The receiver converts the manifest list to an RTP sequence number, so we can track the incoming UDP packet. And if it wants to do a switching, then we transform the problem to RTP. We create an ARQ request for that range, convert it back to UDP, slice it in, and we have a seamless switch. This is how it will look like. Just like before, but the downstream is UDP with manifest, which is a very low bitrate type of information. We have a backup DR, and now we can do a DR based on RTP, send it to the receiver, and everything is UDP based. Now, many applications that still would require the use of UDP because of encapsulation. Now with DVB-NI coming into play, that's another thing that can use this capability. Well, thank you.
All right, thank you, Adi.